Welcome, ladies and gentlemen, to this video lecture. Okay, so now we have seen that with Taylor polynomials we can work out approximations of certain numbers. So for example, in our previous example we worked out an approximation for the cube root of 7 using the Taylor polynomial of the cube root function about 8. And why did we choose 8? Because at 8, well, the cube root of 8 is 2, and it is easy to work out the derivatives of the cube root at 8, and to work out the values for the derivative of the cube root at 8. And using those numbers that we can work out, we can use that to give an approximation for something like the cube root of 7. But now note that it is only an approximation. It is not the exact value. Okay, so we would like to quantify how close are we to the exact value. So we would like to be able to say with certainty that we are within, so our approximation is correct up to, let's say, 5 digits or 100 digits or 1,000 digits. So we would like to say with confidence that our approximation is accurate within this bound. So we need to be able to say something about how big is the error that we are making. And this is the theme of the next couple of lectures that we are going to discuss. So let us just define what we mean by the error. So let's definition. Let I be an open interval. Let f be defined on I. Let a be any element of I, and let Pn denote the nth Taylor polynomial of f about a. Okay, then we define the following function. So En on the interval I to R as what? We define En as the difference between the actual function value and the approximation given by the Taylor polynomial, and this is for all I in the interval I. So let us give this function a name. We define the error function, the error En as that. And all that this is, it is the difference between the actual function value and the approximation. So this is essentially the sign distance from your approximation to the actual value. Or in other words, it is the error that you're making. How big is the error that you are making in your approximation? Okay, So here we have now defined the error. Okay. It is quite amazing that we can actually give an expression for the error, and we can use that to quantify how big the error is that we are making. So this is the theme of the next theorem. So theorem so let I be an open interval and let f be defined on I and let f be n plus 1 times differentiable on I, with the n plus first derivative continuous on I. Then with A in our interval I and with Pn the nth Taylor polynomial of f about A, we can actually quantify what the error is. So the error that we are making, and remember what this is just the function value minus the nth value of the nth Taylor polynomial. This is equal to the following integral. It's equal to the integral from A to x the following fnt over n factorial x minus t to the n dt. So we actually have an expression for exactly what the error is. Okay. So in the next video, we will go through the proof of this theorem. Good, I will see you in the next one.